Namaste everyone. This video is going to be crazily long, so I suggest you to move forward, fast forward or fast rewind to whichever places you find a little confusing. You can just skip the portions that you're already good at and watch the portions that you feel doubt of. So without further ado, let us jump into the problem. Namaste everyone. Here is a problem from the previous papers of Osmania University. One of my students actually requested me to do a video on this. So as you can see, this is a problem on Truss. The diagram was not clear in the examination paper that he had sent me, so I was able to recreate it over here like this. So as you can see here in the question, we have to find forces in all the members of the truss, and we have to use the method of join. So since the problem is going to be very long, let me just walk you through the steps we will take to solve it. Step number 1, find reactions at the supports. Step number 2, take the FBDs of joints with 2 or less unknowns, and that is unknown forces, and we have to find them. And step 3, that is after having solved all the forces, note them down in a table. Now let's go ahead with the first step. So as I told in the first step, we will have to find the unknown reactions, the reactions at whatever supports we have. Those we will have to find. So while doing this, the whole of truss has to be considered as a single body, and we have to take up all the forces on it, and we'll have to find the reactions RA and RB. Since all the forces here are vertical, let's first take up the sigma V. RA is positive upwards, so is RB, and the remaining all forces are downwards, so we have to take them as negative. Of course, this being a problem of statics, the total has to be 0. This gives us the sum of RA and RB as 550 kilonewtons. Let's call it as equation number 1, and let's go to the next equation. Sum of horizontal components is going to be of no use to us because there are no inclined forces here. So we will have to take up sum of moments, and one of the 2 points we can take as the reference, either A or F. I'll just go with A. Now I have to take moment due to all the forces acting on this body about the point A, and I have to add them together. RA is the reaction which is passing through A, so its perpendicular distance is 0, and hence it will not have any moment. So the force of 300 kilonewtons is at a perpendicular distance of 3 from the point A, and it is rotating the frame clockwise. So let's take it positive. The force of 200 kilonewtons is located at a perpendicular distance of 6 meters, and once again it's rotating clockwise. Same goes for the other force, that is 50 kilonewtons. Distance is same, and it is also rotating it clockwise. The reaction RB, however, will try to rotate the frame counterclockwise, hence we have to take its moment as negative. The moment itself will be the force RB multiplied with its perpendicular distance, that totals to 9 meters. Once again, this being the problem of statics, we will have to take the total to be equal to 0. Now in this equation, RB is the only unknown, and we have to find it. So let's send it to the other side, find the remaining terms, and then divide that by 9. So here I have done the calculation. I have added all the forces here, and then by dividing it with 9, I'm getting the answer as 266.67. So RB value, we will get 266.67 kilonewtons. Let's call it as equation number 2, and by substituting RB value here in equation 1, we will get the value of RA as 283.33 kilonewtons, of course. Now note down the reactions in the figure like this, and that completes our step 1. For step 2, we will have to take the FBDs, that is the free body diagrams of joints. One of these joints we'll have to take, either A, C, B, D, E or F, and we have to choose it such that less than 2 forces, 2 or less than 2 forces are unknown at that point. So it's basically a very good idea to start with the corners, which are the supports themselves. So I'll just start by taking this particular joint over here. And now I have to put all the forces here. So now this force RA we were already able to find in the step 1. the two other forces which are acting in the beam AC and AB. So those two are unknown. This is the force in AB and this here is the force in AC. Now before finding the forces, we first have to find this angle here. So in this triangle ABC, we know the opposite and adjacent. So alpha will be equal to tan inverse of opposite length, that is 4, divided by adjacent length, which is 3. That gives us the angle as 53.13, of course in degrees. Now let's take the sum of all the vertical components. RA is of course acting upwards, so it has to be taken as positive force. FAC is horizontal, so it will have no role to play in the vertical components. FAB, we have to take component of that, and that component will be FAB sine of alpha, and that will of course be acting upwards, so we have to take it as positive. So because this joint is not moving as itself, so again that joint is at equilibrium, so the net force has to be equal to 0. So now using this we can find the formula, the value of FAB, that will be minus 283.33 divided by sine alpha. Calculating that gives us minus 354.16 kilonewtons. Of course this is negative. Now here there is one interesting thing to know about the negative and positive conventions. By default we are taking all the arrows away from the point, which means we are assuming all of these to be in tension. So if the result comes out as positive, then we have to assume that whatever force is acting in that bar, for example here we have found the force in AB, so the force in AB is coming out as negative, which means it is not tension. Because it is negative, that means the force acting there is in compression. Okay, so whatever values we get negative in the unknown forces, those will be in compression, and whatever values we are getting in tension, that will be of course positive. Fine. Next, of course, let us take the sum of all the horizontal components. Now FAC is horizontal, so all of it will actually come here, and of course it is acting in forward direction, so it's positive. Now the component of FAB, so FAB, its component in horizontal direction will be cos alpha. Now according to the diagram here, because the force is acting away from here, so the component will be acting on the right side, so hence it has to be taken as positive. Of course, because the joint is not moving, it is static or in equilibrium, the total has to be 0. The value of FAB we can substitute from what we found. Be careful about the sign convention though. Here, because FAB itself is negative, the positive will actually change to negative, and cos of alpha, this total has to be 0. So FAC we can calculate by sending this whole term to the other side. Calculating that will give us this result, 283.33 kilonewtons. So once again the result is negative, meaning it is actually compression. So here I have written the two forces that we just now found for your convenience. Now let's consider the next joint where we can find the unknown forces. So adjacent to A we have the joint C, wherein there are 3 unknown forces. So we cannot take this as our next target. Watching here, we can see that one force has already been found and there are 2 unknown forces here. So this would be the right joint for us to take. So let me now take the free body diagram of that particular corner and start solving the problem. Once again, wherever the joints, wherever the beams are cut, we should assume that the forces are acting away from the point. This value here we already know, that's minus 354.16, and the other 2 forces are not known to us. So this will be the force in BC and this will be the force in BD. Now once again, before starting the solution, we should know the angles. So these 2 angles are to be known. So the angle here will be same as alpha, because we can see here Okay, you can see here that these two angles become alternate interior angles for the parallel lines, and hence alpha will be same here. Coming for this angle, let's call it as beta, so that we can find by using this angle here. Fine. So let's take up this triangle DEF. In that again we know the value of opposite and adjacent, and using that let us find it. So the angle beta will be equal to tan inverse opposite length, that is 2, divided by adjacent length, that is 3. That gives us an angle of 33.69. And of course alpha we had calculated in the before as well. Its value is 53.13. Now once again we will have to apply the equations of equilibrium here. So in this case let us start with sigma h, because FBC is vertical and we want to ignore it in our first equation. We want only one variable in our equation at a time so that we can easily solve it. So of course 300 kilonewton and FBC both are vertical, they will not have any effect in the horizontal direction. So we'll have to take up this force over here, minus 354.16, multiply this with cos of alpha, that will give us the horizontal component of this particular force, and then we'll have to take FBD, multiply that with cos beta, that will again give us the horizontal component of FBD. Now in the diagram we are assuming it to be acting on the right side here, and hence the horizontal component will come out as positive. So that when calculated we get FBD value as 255.39 kilonewtons. Next we have to of course take all the vertical components and add them. So 300 is acting downwards, so it has to be taken as negative. FBC is also acting downwards, so once again negative. FBD will have its component acting downwards, so negative. FBD, and for taking component we'll have to multiply sine of beta with this. Then going to the other side we have force minus 354.16, and of course we'll have to again multiply sine alpha with this, so that we can get the downward component. Here there is one more thing we have to note, that because from the diagram here the arrow is acting downwards, we will have to apply one more negative sign over here. So this value as a force we have directly taken here from the diagram, and this negative sign is for the diagram, the arrow. Once again, because this is a problem of statics, the total has to be equal to 0. So that when we calculate here using the calculator we get this value here. You can pause the video to check out the calculations. Just note down this, minus 158.34 kilonewtons of course. So once again we have to understand, because the value of FBD is coming out as positive, this is in tension, and because this one FBC is coming as negative, that means it is in compression. So the values that we just now found I have written here on the diagram for your convenience. Let's go for digging out which joint to take next. So even though at this point C can be taken, because there are again only two unknowns, but at this point it is better off to actually start from the other end, because that provides us with much simpler ways of solving. And of course you must be knowing this already, that no matter what is the approach you are taking, the final results are going to be the same. So let me just take the free body diagram of that corner F and start solving. As usual, all the unknown forces we will assume to be acting away from the corner, and we will give them names. This is FDF or FD, whatever you want to call it, and this force here is FEF, the force in EF. Here the angle beta, if you remember, we had calculated it to be 33.69 degrees. Now let's apply the equations of equilibrium. In this case I want to start with sigma V, because that will help me avoid the horizontal force FEF. So first I have to take RB, that is 266.67, and of course because it is acting upwards we have to take it as positive. Then we have to take the component of FDF, and because it is going up away or opposite, we have to of course take it as sine of beta, and of course this component will be acting upwards, so it has to be positive. Again, the total has to be 0 because it is in equilibrium. Now doing the calculation for FDF, we get its value as minus 480.7. Now of course, because it is negative, that means it is in compression. After that, we'll have to go ahead and take all the horizontal components. So FEF is acting on the left side, so it has to be taken as negative. And the component of FDF, of course, to get the component, we have to multiply cos beta. And of course, because this is acting on the left, so we have to take it as minus. Once again, the total has to be equal to 0. Now let's substitute the value of FDF. So minus FEF, this minus as it is, and the value of FDF itself is again minus, and of course the cos of beta value being 33.69, total has to be equal to 0. Now the minus into minus will cancel out the negative sign, and solving for FEF, we get this result. Now of course, because it is positive, this is of course in tension. Once again, I have noted these two forces that we just now found here on the diagram. That leaves only 3 beams in which we have to find the stress. And joint E seems to be the most simplest of the joint for us to take up next. So let me take the free body diagram of the joint E and put down all the forces. 2 of these forces are already known to us. This force here is the force in ED, and this force here is the force in CE. Both of these are unknowns and we have to find them. Equations will be very simple. Sigma V will just have FED acting upwards and 50 acting downwards, total equals 0. FED will give us 50 newtons. Of course, because this is positive, it will come out in tension. Then sigma H will give us 400 newtons acting right side, and FCE acting on the left. So total of course is to be 0. So that leaves FCE value for us as 400. Of course, even this is positive, so it will be in tension. Now that leaves us with only one of the truss, that is CD, in which we have to find the stress. So we can take up any one of the sides, any one of the joints. Either we can take up C or we can take up D. But the point D will provide us with a lot more of complications than the point C. So let's go ahead and take C. So this here is the free body diagram of the point C, the joint C. So here I have noted down all the notations for the forces, and we will need this angle here. So in the main truss, we can see that angle is appearing over here, and you can see that these two triangles are exactly symmetric, actually congruent. So the angle beta will appear here as well. So the same angle beta will be here. So here, since there is only one unknown force, we can either go with sigma H or sigma V. But since sigma V is helping me avoid 2 of the forces, I'll just go with that. I'll go with sigma V. So we can see the force FBC is acting upwards, so it's positive. And the component of force CD we have to take. Since it is opposite, we have to multiply this with sine of beta. And of course, in the diagram, we can see it's acting upwards, so it has to be positive. The total, of course, has to be equal to 0 because it is in equilibrium. Now let us substitute whatever known forces are there. So we know here it's minus 158.34 plus FCD is something we have to find, and sine of angle beta. Beta, of course, being the angle 33.69 degrees as we found earlier. This total has to be equal to 0. So doing calculations for FCD, this is what we get. Of course, this is positive and hence tension. Let me put this force where it belongs. Okay. So that's it. We have found all the forces in all the trusses, all the elements of this truss, and this is how it appears. So if you want, you can just put them down in the form of a table. That's what I have written in the step 3. Okay, so step 3 we were already covering by doing each joint at a time, and I was already noting down all the forces in the diagram. So in the diagram, whatever forces are positive, they are of course in tension. Whatever are negative, they are in compression. You can just put that convention down here. You can just write here as positive means tension and negative means compression, and that I think should be an enough of indication for the examiner as well if he intends to find out what it is that he is doing. So this is how the whole problem looks like. Okay, we're solving the part of these things and placing them at different locations so that all of these could be actually assembled to the correct point. So this is where we started. This is where we actually started, and after this we went towards this direction, then we saw this, then we saw this, then we went here, and finally the last step we went here. So if you want, you can pause the video at different points, and of course you can make a forward, fast forward or fast rewind, check out whichever part of the video you don't understand. And if you think that there was some mistake in this, or if you want to find out in more detail anything about the video, please let me know in the comment section below. So thanks for watching this video, and if there is anything, of course, I'm here to help you out. Thank you.